Subdivisions won't change that limit. Will not change the limit when f is continuous. Alright, so that's all very straightforward, you've all seen that. And the reason I wanted to just briefly go over it is because we extend those ideas when we're thinking of integrals in higher dimensions. So now we're going to consider this in 2 dimensions. So we consider a similar approach when informally defining the double integral. So let's think about what we're doing now. So let's suppose we consider a region of the plane together with some function. So together with a scalar field now, which we're going to call psi, which will be a function of the coordinates in the plane x, y. Okay, so we're going to have the plane. Here's x, here's y, and we're going to integrate over some region in the plane, which we're going to call R. Our region is R. So if I'm thinking of this in terms of its sort of physical interpretation, so if I have x and y now in the plane, and I have my third dimensional plane up here, and psi is some scalar field, it's a surface. Here's where I challenge my ability to draw, something like that, suppose that's phi. And what I want to do is integrate that function over some region in the plane. Here's my R, I want to integrate that function over that region. So what I'm doing now is computing the volume underneath that surface. So we do exactly the same thing. So this time, instead of partitioning the line into small intervals of width delta x, we partition the plane into small elements of a given area. And you can think about dividing this up into regions and then summing, playing the same trick, summing all the volumes that are given between the surface over that small element in the plane, sum them all up, take the limit, and that is the double integral. So we might suppose this is width delta x, delta y. And we can say, again, we need to define some value for the scalar field. So let's suppose the scalar field psi takes the value, I'm going to call it psi with subscript I, in the centre of the iPhone. Then, on partitioning the plane, region R into smaller and smaller sub-regions. And then taking the limit this time as the region, the area of that region tends to 0. So taking the limit as delta A tends to 0. So I should have said it up here. So I'm going to define delta A to be delta X, delta Y. It's just the area of that little region. Width delta X and height delta Y. So then we can define the double integral. So we have the limit as delta A tends to 0 of the sum. So now I sum over, let's suppose there are n subregions. So I sum from I of the scalar field at the centre of the subregion times delta A, which is the same as saying the limit delta x, delta y tends to 0, I equals 1 to n of psi I delta x delta y, and we define that to be, so this is definition, the integral over the region R, and to denote the fact we're integrating over an area, not over a single line or a single variable, we use a double integral of psi dx dy. And in the last course you did last term, in introductory calculus, you computed a lot of these double integrals. So this is the informal definition. Of a double integral, and it represents the volume and the integral is the volume under the surface. So again, we have all the usual things. We want to make sure that the limit exists, and it turns out that if psi is piecewise continuous, and R is a suitable region, which covers a lot of things, a suitable, well-behaved region, there are no difficulties. And in this course, these are the sorts of functions and domains that we'll be considering. Okay, so that's a whistle-stop through how we think about double integrals and how they connect to single integrals, and it's going to be the focus of our lectures in the coming weeks. So these double integrals have a number of properties which are useful to note and exploit, and there's even more in the online lecture notes that you want to take a look at. So the following properties are inherited from integration with respect to one variable. So the properties I'm going to write down are often useful when you're trying to think about careful and more straightforward ways to compute double integrals. So we're going to see examples where it doesn't matter which way I integrate, whether I integrate first with respect to x or then with respect to y or vice versa. But some methods are more advantageous and mean you have to do less work. And these properties can also be exploited to allow you to essentially do less work. So we're going to think about sensible ways to compute these integrals, exploiting various properties. So let's start with the property of linearity. So let's suppose a and b are just constants. So then we have that the integral over r, so some suitable domain in the plane of a times some function of f of x and y plus b times a function g of x and y, all integrated over the plane to A, over the region of interest. Well, that's just the same